a tale of two zeros. So in this clip, we're going to establish that 0 is a killer as both an element of the field and as an element of the vector space. So remember, every field has a 0 and every vector space has a 0. So let's see. So first one, for any element of the vector space, if we scalar multiply it by the scalar 0, it gets dead. All right, so key point here is that this 0 here is a number. And you knew that in advance, right? Because v is a vector. So the only thing you can multiply a vector by is a scalar. So you know that this 0 has to represent a scalar. Now, by the same token, what is this one over here? Is this 0 the number or 0 the vector? Well, a moment's reflection tells you that, oh, if I scalar multiply a vector, I get a vector. So this 0 over here must actually be a vector. Okay. And so that's coming from the fact that if you scalar multiply by a field element, you get a vector. So the output is a vector, something in V. All right. So this looks obvious. So maybe the first thing that I should point out is that this, in fact, needs proof. It doesn't actually, it's not immediate from anything that we've done so far. Okay. So let's look at the proof of this cute little statement. So suppose we take 0v. All right. Well, I can rewrite this as 0 plus 0 v. And this comes by using the additive identity property in the field, right? So in the field, 0 added to anything is just the thing I started with. So in this case, if I add 0 to anything, then the sum is going to still be 0. Okay? And then I can use distributivity in the... so we've got 0v plus 0v, and so that's by distributivity, one of the versions of distributivity. And then if I add the additive inverse of 0v to both sides, then on the left side I'm going to get 0, and on the right side I'm going to get 0v. So I'm just essentially canceling these two off by adding minus 0v, the additive inverse of whatever that crazy element is, to both sides of the equation. And then that last thing is the thing that we wanted to prove, so I get an end of proof symbol, and I'm happy. All right. So that's 0 as the element of the field kills vectors. And now we can say, we'll look at the other one, and that is for any field element lambda, if I scalar multiply the 0 of the vector field, then I get the 0 of the vector field. So in this case here, the 0 refers to a vector on both sides of the equation. Okay, so let's see. Switch back to black ink. Okay. Proof. How do we prove this? Well, let's see. So I'm going to start with lambda 0 again, and I can do the same thing. So lambda times 0 plus 0 is the same thing as lambda 0. And now, even though the equation looks identical, it's actually the fact that I'm using the property of additive identity in the vector space, because in this case, both of these two zeros here are vectors. All right. And so then I can use the other form of distributivity, distribute over a sum of vectors. And then I can, again, add lambda 0 to both sides and cancel. And so I did to both both sides. Okay. And then I got where I'm going. So again, I get a box. The end.